how this kind of field theory on non-commutative space can arise starting from a lowest lambda level projected a simple microscopic Hamiltonian. And I wanted to say it's a technical subject, but I've tried to make it pedagogical. So please stop me at any point if you feel like I'm going too fast or you didn't catch something that I said. Before we get into the details, let's start with a bit of a bird's eye view, and which is how do we understand the low energy long wavelength properties of quantum matter? We heuristically just have this classification based on the number of low energy states. We first divide it into gap states and gapless states, depending on the lowest excitation energy. And within gapped and gapless states, we further divide it into something called liquid and non-liquid states. This is non-standard terminology, but I like it. The idea of a liquid state is that the effective theory at low energies does not care about the microscopic details. So if you start with a lattice, the low energy theory will not care that, okay, you really started from a lattice. Ultimately, the low energy theory will only care about the smooth manifold that your lattice lives in. This is in contrast to non-liquid theories, where the effective theory will remember some UV information, such as lattice details, etc. Another way of saying this is that non-liquid theories have UV-IR mixing, whereas liquid theories have a good description in terms of a quantum field theory. A good example of a liquid state is a paramagnet, SPT states, topological orders such as toric code and fractional quantum Hall. A liquid gapless state would be a CFT, such as the Ising CFT, or a semi-metal, such as graphene. A non-liquid gap state would be a fracton, where your ground state degeneracy scales with system size and it has weird properties. A non-liquid gapless state would be a metal or systems with a Fermi surface, where you have a large number of low energy degrees of freedom. I want to emphasize that these liquid states are well understood within our current framework of quantum field theory, whereas these non-liquid states are much more complicated, and we won't worry about them in this talk. So the next question I want to ask is, how do field theories arise in a typical condensed matter model? The story usually goes as follows. We start from a regularized lattice model where we have finite number of degrees of freedom per unit cell. And then we argue that at low energies, we can coarse grain away the microscopic details, and we can end up with an effective field theory of the long wavelength low energy physics, which will ultimately forget about all the lattice details. A simple example is the theory of phonons in one dimension, where you have different ions connected by some potential. And the idea is that at low energies, only long wavelength fluctuations will ultimately matter. And we can forget about the individual displacements of each of the ions, and describe it using some smooth function in space, which fluctuates at momenta much smaller than lattice spacing inverse. Is that clear? Again, please stop me with any questions, and I will pause in between in case you have to think about questions. Okay. So now that we have this big picture, let's focus on a particular field theory. And the field theory that I choose to focus on is that of superfluids. The reason I want to take a few slides to talk about superfluids is that we have a field theory for superfluids. We understand exactly the relationship between the microscopic degrees of freedom and the effective field theory. The goal of this talk is to get a similar understanding for the lowest lambda level superfluid. Okay. So superfluidity was first discovered in helium-4 at low temperatures in 1937 in Russia by Kapitsa, and independently in England by Allen and Misner. It's a very interesting subject experimentally, but for theorists, it's a very difficult problem because you really have a pool of helium atoms which are very close to each other, which means they're interacting together very strongly, and which basically means that you have no small parameter to do perturbation theory over. The first major progress came with Landau in 1941, where he postulated that superfluids are described by a classical wave function, psi of x, which minimizes the Ginzburg-Landau free energy. I'm fudging history a little bit, but This is the main takeaway. Uh, so you have some free energy functional of the classical wave function psi, and the configuration that minimizes this free energy wave function will describe your superfluid. And Landau also gave us a dictionary, which tells us, okay, how do you describe the density and currents of the microscopic bosons in terms of this classical wave function psi? This was very successful. You could predict a lot of properties of the superfluid using this formalism. But as a theorist, it leaves you slightly uncomfortable because we have no idea where psi comes from. All we know is that there's a bunch of bosons which are interacting with each other very strongly. And then Landau comes and tells us that it's described by a classical wave function, and it gets the correct answers. But how do you justify that? Okay, this is truly what's happening in this case. Well, why does this work? Before we explain why Landau's theory works, I want to emphasize that Landau's theory is a really good effective field theory because it does two things. One is that it coarse-grains away the short distance features, which we ultimately don't care about. So if we want to write down an effective field theory describing the long wavelength, low energy physics, we ultimately don't want the theory to keep track of all the microscopic details, such as where is each atom sitting at each point in time, etc. And Landau's theory does that. It doesn't retain any information about the individual bosons or the exact nature of interactions between them. And here I will denote it mathematically that the UV cutoff inverse is greater than the atomic size scale. Okay. The other thing which Landau's theory does well is that symmetry must be manifest. The idea is that if there is a symmetry in your theory, we know that the effective theory should also have the same symmetry. In which case, if we want to write down an action, we want to work in variables where the symmetry acts naturally, which is helpful because we want to write down an action in terms of symmetry covariant objects. And this also works for Landau's theory because the U1 symmetry, which conserves particle number, which is the crucial symmetry for the superfluid, acts very nicely on Landau's classical wave function. And Landau's theory is a good effective field theory because it does both of these. It coarse-grains the degrees of freedom very well, and it retains the symmetry manifestly. Any questions about that? Okay. So going back to the question I raised earlier, Landau makes a lot of predictions using this classical wave function psi, but where does this wave function come from? And it took 6 years for us to understand this. It was understood by Bogoliubov in 1947. And the hero of this story is the bosonic coherent state, which you learn about in graduate school. It's a family of states, family of many-body Fock states, defined by the following operation. First, let me clarify some notation. I use this double ket symbol to refer to Fock states or many particle states. And the zero state is just the bosonic vacuum, the state without any bosons. And the coherent state is defined as this exponential of the boson creation operator acting on the bosonic vacuum. If you Taylor expand the exponential, it's just you apply the boson creation operator for the single particle state psi of x, and you form a coherent superposition of different occupation numbers of the same single particle state. This is very useful because it has nice properties. The field annihilation operator is the state is an eigenstate of the field annihilation operator with the following eigenvalue, and you can construct trace operators and so on. Now that we have this technology, we can essentially derive Landau's theory from microscopics. Let's assume some weakly interacting boson problem, which is described by the following Hamiltonian. You have a kinetic energy term, you have a chemical potential, and you have some short-range interaction, essentially contact interaction. The partition function is traced to the trace of e to the minus beta h. You do the standard trotterization. You split the e to the minus beta h to n parts, take the limit n going to infinity, and you insert resolutions of identity using the coherent states at each step. And then using the nice properties of the coherent state, you can show that the partition function can be written as a path integral over complex fields living on spacetime with the following action. And we call this object the action. And we know that ignoring fluctuations, which effectively means doing mean field theory, recovers Landau's effective theory of the superfluid. So I did all this just so that you get a template for what I plan to do for the lowest Landau level superfluid. The idea is going to be that there is this effective theory for the lowest Landau level superfluid that works really well. We don't have a good understanding of how to relate the microscopic fields, in this case, the boson annihilation operators, to this classical wave function or effective description, which in this case is psi. And in this work, I essentially develop a coherent state path integral that can connect this effective field theory that supposedly seems to work and arrive there starting from a more microscopic Hamiltonian. So this is sort of a good stopping point. So any questions so far, I can take them.
Yeah, so you're kind of implicitly doing Hubbard-Stratanovich, or I'm not sure if this is exactly it, or like why do you have to do trotterization if you can just do HS or HS sort of decoupling of the interaction?
Sorry, I didn't catch the last part of your sentence.
There's no HS decouple.
I mean, you can get the same answer with Hubbard-Stratanovich, right?
Yes, sure.
No.
There's no Hubbard-Stratanovich here.
Well, psi is the auxiliary field in a way.
Yeah, but psi is introduced in the way that psi is a coherent state, right?
Yeah.
Yeah, it's a many-body like bosonic coherent state.
At the end of the day, you just do the path integral over it and it's
Yeah.
a field. Like,
So-
That's the field, yeah.
Right.
It's a classical field with some interesting dynamics.
well, my point is that you can get to the line before the last one just by doing Hubbard-Stratanovich, or you can do it with this coherent state. Is it important that you're choosing this way?
So what I know of Hubbard-Stratanovich is you start from a path integral theory, and then you introduce classical variables using Hubbard-Stratanovich, right?
Yeah.
Here, it's more elementary. You start from the Hamiltonian, and you do the standard trotterization to get to the field theory. That's all I'm doing.
Okay.
Okay. Any other questions? Okay. If not, let's move on. So in this talk, I'll be talking about rapidly rotating superfluids. This is a pretty old subject where we have done experiments that shows that if you take a superfluid in a trap and you rotate the trap very fast, it develops vortices because superfluids cannot have can only have quantized vorticity. It cannot rotate smoothly. And experimentally, we see that it forms a triangular array of vortices. And as a theorist, we can ask the following simple question. This state is a superfluid, so it breaks charge conservation symmetry spontaneously. It also breaks translation symmetry because it forms a vortex lattice. So you expect 3 Nambu-Goldstone bosons, 2 for translation and 1 for charge conservation. But if you do the calculation, or if you do numerics or the experiment, you will find that there's only 1 Nambu-Goldstone boson with dispersion going as omega goes as k squared, which is non-standard. This is also known as the Kachenko mode. So one of the goals of this talk will be to explain why there is only 1 Nambu-Goldstone boson instead of the naively expected 3, and also why it has omega goes as k squared dispersion relation. A recent breakthrough in this subject was achieved a few years ago when the following authors wrote this paper, which effectively describes a non-commutative field theory of this number Goldstone boson, the Kachenko mode. Their claim was that you can write down a partition function where the degree of freedom is a non-commutative field, which just means that it's a field phi of non-commuting coordinates, x hat and y hat, which have the following commutation relation. So it's not like regular space where x and y commute, but x and y don't commute, and it has this non-commutativity. And the claim is that you can write down a path integral over such a non-commutative space and recover all the properties of this Kachenko mode. And they also show us how the symmetries, namely charge conservation and translation symmetry, acts on this non-commutative field. So the goal of this talk will be to understand microscopically where such a field theory living on non-commutative space, where your x and y don't commute, can arise. So let me quickly review the physics of this problem. So you have a superfluid in a trap, in a harmonic trap, which means that the trap, the potential increases quadratically, and you rotate the superfluid at some angular velocity such that the centrifugal force created by the rotation exactly cancels the trap potential. And so the centrifugal force and the trap potential exactly cancel. You're left with the Coriolis force, which has the following expression. You can interpret this as the Lorentz force due to a magnetic field. And in this case, you have 2m omega. Omega is the rotation frequency that acts like an effective magnetic field for your problem. So really you can really imagine that you just have a superfluid in a strong magnetic field. It's the exact same physics. And to give you some idea of what we are trying to achieve, so as we saw in the picture, we saw that there was an array of vortices which are separated by magnetic length. We know that the Schrodinger's equation essentially describes everything starting from each individual atom. We know that Landau's theory gives you an effective description outside the atomic size. But we don't have an effective description of the physics much larger than the individual vortex separation. So this is what we are trying to explain you. This is essentially the Kachenko mode. It's like long wavelength fluctuations of this vortex lattice, which naturally will exist at length scales much larger than the individual vortex separation. And the effective field theory we want lives at this length scale between the vortex separation and the system size. And since in principle, Landau's theory explains everything from this length scale to the largest length scales, maybe we can start from Landau theory as a starting point to understand what the effective field theory of the vortex lattice might look like. Is that clear?
So is it a very fine-tuned system in order for the centrifugal force and the harmonic trap force to cancel?
Yeah, so you have to fine-tune one parameter. That's right. Okay. So let's go to Landau theory, which we understand very well. The only difference now will be that you have this effective magnetic field created by the Coriolis force. We will introduce that as a vector potential, the standard minimal coupling. And let's study this Landau free energy and try to minimize it. And as a starting point, let's ignore the interaction strength G. So if you ignore the interaction strength, this becomes a free fermion problem. It's all quadratic. And you have a strong magnetic field. You know that at low energies, your classical wave function must be a lowest Landau level wave function to minimize this free energy. And the lowest Landau level wave function in the symmetric gauge can be written as some holomorphic function times this factor. Any such wave function, I'll just call psi LLL, just tells you that it's some wave function living in the lowest Landau level. So now that we have minimized over this manifold, and we have a large degenerate lowest Landau level space, we can add the interaction strength and ask, okay, now if you also have this weak interaction on top of the lowest lambda level, what does the minimum energy configuration look like? And if you restrict to the lowest lambda level manifold, the kinetic energy becomes trivial. It just gives you a contribution half h bar omega c, and the minus mu remains the same. And you have free energy of a lowest lambda level wave function given by this factor times psi squared times the interaction times psi to the 4. Is that clear? So we want to minimize this. This is a very non-trivial problem because you're minimizing over the manifold of lowest lambda level wave functions, which is not exactly easy to do. But there's a very good intuition for this, which is that this is just density. This is just density squared. You want to minimize. Okay, I'll assume this factor is negative because I want a non-trivial solution. You want to maximize density while minimizing density squared, essentially. And intuitively, you can sense that this means that you should minimize the variance of density, right? Variance is like expectation value of density squared, which means that you want to spread out the superfluid density as uniformly as possible. That is how you will minimize expectation value of rho squared. And suppress the variance of density over space. And it turns out you can do this. This was done by Abrikosov. And the answer is that you want to arrange the zeros of the holomorphic wave function describing your lowest lambda wave function in a triangular lattice. I have just plotted the value of the wave function squared here. It's a simple triangular lattice. The separation between the vortices is order magnetic length. And in fact, these are the magnetic lattice translation invariant wave functions in the lowest lambda level. I'll explain in a bit what that means. But any questions so far? Yeah. So here I have to introduce some single particle physics of the lowest lambda level. So in the lowest lambda level, you have these operators known as guiding center operators, which are essentially the projected position operators. So you take the regular position operator, you project it to the lowest lambda level, and you get these guiding center operators, which have the following expression in a particular gauge choice. The important point is that they have a non-trivial commutation relation, which is x hat y hat is minus I LB squared. LB is the magnetic length. And because of this commutation relation, these guiding center operators have a dual role, which is because they are the projected position operator, x hat, as you would expect, it measures the position along the x direction. But also, if you look at this commutation relation, this should remind you of x hat comma p hat is IH bar, which also gives you some intuition that x hat should generate translations along the y direction. Because if you think of y as a position operator, x is behaving like a momentum operator in the y direction. So it really has this dual role, and that's one of the most important features of the lowest lambda level, that position in the x direction is the same operator as momentum in the y direction. And because x generates translations along the y direction, if you exponentiate it, or in general, if you exponentiate some e to the I k dot r, it acts like a translation by a vector that is 90 degrees rotated by 90 degrees rotated to k. So because x generates translations in the y direction, y generates translations in the minus x direction, and so on, you can show that this operator generates a translation by LB squared times wedge k. Wedge k just means k rotated by 90 degrees. And if you remember from your graduate QM, these translation operators do not commute because of the Aharonov-Bohm phase that you pick up because of the magnetic field. And you can show that if you multiply two translation operators, they are equal to the total translation operator given by k plus k prime, but they also pick up a phase, which is this e to the ILB k wedge k prime over 2. And the wedge product, if you're not familiar, is given by this expression. Just tells you the area enclosed by the parallelogram found by k and k prime. This also gives you the usual intuition that magnetic translation operators commute if their translation vectors enclose an integer quantum of magnetic flux. In the k-space language, that would mean that k wedge k prime must be 2 pi times some magnetic length factor times an integer. If this condition is satisfied, then we know that these two translation operators commute. So in principle, we can choose two values of k, k1 and k2, such that it encloses exactly one magnetic flux, the corresponding translation operators. And now that these operators commute, you can simultaneously diagonalize them. These are effectively lattice translations now. If you diagonalize and you look at the eigenstates, these will be your magnetic lattice translation invariant wave functions. I think first described in a famous paper by Haldane and Rezai. It's a unique wave function. Oh, sorry. It's wave functions which are eigenstates of both e to the ik1 dot r and e to the ik2 dot r. And you can simultaneously diagonalize them because they commute. Now, moving forward, let's choose a special state as a reference state. This will be clear in a second why I'm doing this. And the reference state, by choice, it's an arbitrary choice that I'm making, will be the state that has eigenvalue 1 for both of these operators. I will call phi 0 that has eigenvalue 1 as a reference state. And I will call phi k, where you should think of k as now a momentum index, as e to the ik dot r, where k, imagine k to be some small momentum, are the translated vortex lattice states. We know that e to the ik dot r translates by a vector perpendicular to k. And if k is small, it's really a small translation of the vortex lattice. And you can check that if you look at the action of our original lattice translation operators on this new state phi k, it picks up e to the minus ik dot a1. I should have repeated what a1 means. A1 is the lattice translation corresponding to k1. Sorry about that. What this tells you is that phi k really is analogous to a block state with momentum k. If you imagine a1 and a2, which is given by k1 and k2, which is the two translation operators here and here. This is a1, a2. If you take this new state psi k, which is a small translation of our reference state, and apply the translation operator along a1, you just pick up the momentum factor e to the ik dot a1. Which tells you that phi k are the magnetic block states. It's just analogous to the crystal block states that you're familiar with momentum k. So any questions about that? I think that was a little confusing. Okay. So now, if you must have noticed, this looks very similar to the vortex lattice that Abrikosov solved for in mean field theory. And the reason is that the many-body coherent state corresponding to this reference state phi 0, and a many-body coherent state now means you have many different occupation numbers of the same single particle state phi 0, and you have a coherent superposition across these different particle number sectors. This many-body state will correspond to Abrikosov solution. So just like how in Landau theory, we know that the classical wave functions correspond to coherent state. A coherent state in this lattice translation invariant wave function is really Abrikosov solution. And our goal is to capture the long wavelength fluctuations on top of this many particle ground state. Okay. And before we go ahead to the physics, just some final statements about the algebra of lowest Landau level operators. Again, please stop me if something doesn't make sense. The crucial thing is you have this non-trivial commutation relation x hat and y hat of the guiding center operators, which act completely within the lowest Landau level. A general linear operator in the lowest Lambda level can be written as an arbitrary function of x hat and y hat, which we can now call a non-commutative function because it's a function of two variables, x hat and y hat, which don't commute. This space of functions forms a complex vector space. If you think of e to the ik dot r as basis elements, sorry, there should be an r hat here. Sorry about that. So the claim is that any function of x hat and y hat can be expanded in terms of this e to the ik dot r with complex coefficients f of k. You should just think of this as a Fourier transform. And we know that physically, we should only care about long wavelength fluctuations of the vortex lattice. Short wavelength fluctuations will cost too much energy at mean field theory. So the low energy fluctuations will really be the long wavelength phonon type oscillations of the vortex lattice. And the claim is that the way to construct these long wavelength deformations is to multiply this non-commutative function f of r hat to the reference state phi 0. Recall that f of r hat is an arbitrary function in the lowest Lambda level single particle space, arbitrary operator. But if you want to restrict to long wavelength deformations, the thing we have to do is we have to look at its Fourier transform and impose a cutoff, lambda, such that f hat has support only on low momenta. So if you do the Fourier transform, you say that, okay, for k greater than lambda, which is order magnetic length inverse, greater than lambda, f of k is always 0. You only allow the f of k to fluctuate within some UV cutoff. And there is a physics reason for doing that approximation, which is that short wavelength fluctuations outside the UV cutoff will be energetically suppressed in the path integral, and we expect them to not be important. Is that clear? This is one of the crucial points. Okay, we're really writing down an effective field theory, a description greater than the magnetic length scale. So we don't expect to capture the physics of each individual vortex or at the level of separation of two vortices. Okay. This is a funny slide. I don't expect you to understand everything that's going on here. The takeaway is that I just want you to understand that every operation that you're familiar with for commutative fields, there's an analogous operation for non-commutative fields. It's very simple. There's a very simple dictionary between them. So you have a derivative that acts on plane wave states, pulls out an ikj. Derivative does the exact same thing for non-commutative fields. There's an integral. It behaves exactly the same way. A nice thing about non-commutative fields is that you can think of integrals over non-commutative space as just a regular trace. I introduce a non-commutative function as an operator. It's a function of x and y, so it's an operator. So you can just take the trace instead of thinking of it as an integral. And you can do quadratic integrals. Their Fourier transforms behave exactly like you think. You can do integration by parts. You can write down path integral measures in terms of the Fourier components fk, just like how you do for a regular complex field. You can do a Gaussian path integral where your integral is replaced by a trace, but if you have a Gaussian theory, the expressions look exactly alike. And last and crucially, you can do something called polar decomposition. Let me first explain the commutative context. Any complex field f, you can write that as square root of some density times e to the I phi, a pure phase. The analog here is called polar decomposition. It's a theorem which says that any square matrix can be written as a product of a unitary matrix and a positive semi-definite matrix. So U is a purely unitary matrix. You should think of it as analogous to e to the I phi. And square root of n is a positive semi-definite matrix. You should think of it as a density. And as you can expect, this polar decomposition is going to be important if you want to talk about a superfluid, where the relevant degree of freedom is the phase and not the density. Okay. Any quick questions? I don't expect you to understand the details, just the big picture. It's enough. Okay, so this is an important slide, and here I want to answer why non-commutative fields. Why is that so important? And I don't think it's particularly deep. It's the following. Lowest lambda level coherent states, which I have not defined yet, but you can just imagine these classical wave functions that are lowest lambda level wave functions. For example, the vortex lattice that I just described. It has a lot of microscopic features. So as you saw in the figure earlier, there was like a fluctuation of density at the magnetic length scale, where you have vortices where your density vanish. We don't want to keep track of all these microscopic features. We want to coarse grain over them, right? So imagine we do a path integral and we have such a coherent state, and you have a boson annihilation operator. We know that it will pick up phi zero, right? We know that boson annihilation operator acting on a coherent state just picks up the single particle wave function. The claim is that because of charge conservation symmetry, it always comes with a phi zero bar, because every B comes with a B dagger. But say this phi zero has some long wavelength fluctuation attached to it, given by e to the ikr. Okay, so you have some fluctuating state multiplied by your reference state. And the claim is that if you get coarse grain over the LB length scale, so you're essentially getting rid of all the details that such that your details like your density vanishes at the vortex and so on. You coarse grain over all that. The claim is that this is equal to e to the I k dot r for small momenta k. Okay. Point is, you have this very complicated function which has a lot of short wavelength fluctuations. You coarse grain and throw away all the short wavelength fluctuations. You just end up with this long wavelength e to the I k dot r. And by linearity, you can argue that if you replace this e to the I k dot r by an arbitrary function, it will just be sum over k f of k e to the I k dot r, where I want to emphasize that this is a regular function. This is not a non-commutative function. Is that clear? The idea is that you can coarse grain away all of the details of each vortex. You end up with a regular function that looks a lot like the non-commutative function that describes the fluctuating state.
But this is just an approximation based on your assumption that F has some localization requirement.
It's an assumption.
Like,
mhm.
I remember you take some assumption that, it's the wave functions are only localized, like exponentially localized in some region that warrants this approximation.
So the approximation that I'm making is that only long wavelength fluctuations of the vortex lattice are important in the path integral.
Yeah.
So yeah, this approximation is only valid within that approximation. So you should really think of this as a solution tailored to the specific problem of the lowest lambda level superfluid.
And what about
We know that
this approximation in your equations? You have two approximations in your equations.
right. So yeah, there are two approximations. One is k is small, and one
Yeah.
is coarse graining.
Yeah.
Yeah.
So no, I mean, I'm talking about the approximate like sign in your equations.
Uh-huh.
Like, what does this like? What does it represent? Like, is it coarse graining?
It's coarse graining, and it's also assuming that you neglect higher order terms in k.
Okay.
So within this, so k is not dimensionless, so I should really mean higher order terms in KLB.
I see.
Which is a small number, which is by assumption. And that assumption is motivated by physics.
Okay.
Yeah. So, okay, it seems like you have a fluctuating state described by this non-commutative function f, and it picks out this regular function, which is a commutative field, f of r. So perhaps we can use the commutative field, which is simply the Fourier transform of the f case to label the state f hat. They have the same information because they have the same Fourier components. And the answer here is no. And the reason for this is the second part of this good effective field theory, which is symmetry. So we want to work with variables where symmetry acts manifestly, and symmetry only acts manifestly on the non-commutative fields. You can show that a translation A acts on a non-commutative field F as e to the I k dot r F, where k is 90 degrees perpendicular to A, if you recall, which is very nice. But symmetry does not act as nicely as the corresponding commutative field or the while symbol, if you're familiar with the language. You can do this calculation explicitly, and you can show that a magnetic translation by a vector A takes this function f of r to this complicated, slightly complicated expression. It looks like a translation by A by 2 times some phase factor. It's not at all clear that this is a translation by A. Okay, any questions? Not? Then I will quickly introduce lowest lambda level coherent states. And I hope this will be quick because I'm just going to invoke the analogy to regular coherent states, which we use to describe the superfluids. I will call the phi 0 as a reference state or just 1 hat because it's equal to the non-commutative function just being 1. The idea is you can, just like the regular coherent states, we can define overcomplete basis of coherent states, but now which is manifestly lowest lambda level projective. So they have no occupation in the first, second, third, any of the higher lambda levels. It's completely many body states in the lowest lambda level, but the forms are very similar. So a regular coherent state looks like this. Lowest lambda level coherent state looks like this, where your coefficient now is phi f of r, which is just the wave function formed by acting f of r on our reference state. Similarly, we know that the field operators act on the coherent state to pick up the wave function phi f of r, just like how field operators act for regular coherent states. And you also have a trace over the lowest lambda level Hilbert space. So don't think of this as a trace, think of this as a projector to the lowest lambda level. That has the exact same form as the regular coherent states. I want to emphasize that this trace is subtle because it's a trace over long wavelength states. So I implicitly assume that your momenta are much less than the magnetic length inverse. So this only acts like a trace if you're acting it on a state which is a long wavelength deformation of your vortex lattice. But physics tells us that those are the important states, so we are justified in treating this as an exact trace. Okay, then we do the usual story. We finally have a Hamiltonian. We do the same trotterization process for a purely lowest lambda level projected Hamiltonian. So you have projection to the lowest lambda level here and here. You have a chemical potential, you have an interaction, you have no kinetic energy, as you would expect. And we get a path integral over non-commutative fields. You do the same thing. You take e to the minus beta h, trotterize, insert resolutions of identity, expand, blah, blah. The crucial thing now is that the lowest lambda level projection comes for free. And that's because the resolution of identity that we insert at each step is really a projector to the lowest lambda level. So we can completely forget about that. The path integral takes care of projection to the lowest lambda level. Yes?
Excuse me. The double cats defined here, like what is zero double cat, for example? Is
It's
it a many
the
bodies?
bosonic vacuum state.
Bosonic vacuum state.
Vacuum.
Right?
Vacuum.
Yeah, the vacuum. It's a many body vacuum.
Yes.
And so double cat symbol, the single cat has a completely different.
Yeah, single cat is just the single particle.
Yeah.
wave function.
Yeah.
Oh,
Yeah, double cat is
Okay.
many body.
Mhm. Okay. So I won't do the whole trotterization step. You can just believe me that you end up with something that looks like this. So you have an integral over imaginary time. You have an integral over space, which, if you recall from the dictionary, can be written as a trace. You end up with terms that look like time derivative psi dagger, which must be familiar. There's a chemical potential, there's an interaction. There are other terms which are important, but let's forget about those for now. Let's perform a polar decomposition, which I told you about earlier. We will write F as a unitary times a positive semi-definite operator. And using some physics intuition, we can write N as some mean field density N naught times some small fluctuations delta N. And we can integrate out delta N. We can do this integrating out because we have already learned how to do Gaussian integration for non-commutative fields. When you do this, you get something that looks like a first time derivative u dagger. Recall that u's are now unitary operators. And then there's a time derivative squared term, and you still have these additional terms, which I've kept aside for now. This already captures a lot of important physics. You can show that this is, if you take some kind of a commutative limit, which I will not explain in this talk, this gives us something called a Berry-Lagrangian term. It's a geometric phase. It does not play any role at the linearized theory, but it's very important for capturing transport physics in the lowest standard level. And this second term gives you kinetic energy. So if you've you should just think of this as dou T phi squared, for example. But importantly, I haven't told you how you get dispersions. This is a little tricky. It's actually encoded in these dots, which I did not tell you about. But there's a very simple symmetry / dimensional analysis argument. The idea is the following. Now you've integrated out all the amplitude fluctuations. You're only left with fluctuations which are unitaries acting on your reference state. So the non-commutative function u corresponds to a coherent state, which we earlier defined to be called its u hat. And we know that any unitary in the lowest standard level can be thought of as generating a coordinate map. So you have the guiding center operators x hat and y hat. It maps to some new capital X hat and capital Y hat, which is given by u x u dagger and u y u dagger. This is a unitary transformation, so it preserves all commutation relations. But what I want to emphasize is that just think of this as a coordinate map. R goes to capital R. And we know that the vortex lattice is a triangular lattice. So if we have a coordinate map, we know that to lowest order, what should the elastic energy or the deformation energy look like? It should be some kind of elasticity tensor times strain. And the strain can be calculated exactly. It's the symmetric derivative of the displacement. And the displacement is just small r minus capital R, which turns out you can write it as a derivative of your unitary. Okay, so the important thing I want to emphasize here is that there's a one derivative here, one more derivative here. So strain is really two derivatives of your u field. So if you can plug this back in, you end up with an action that looks like you have a kinetic energy term. You have the strain energy, which is a double derivative of phi. Oh, forgot to mention. In the last step, you write u as e to the I phi. So u is a unitary, which means phi is a Hermitian operator. And you can expand to quadratic order in phi, just like you do in any regular field theory, except now you have matrices. We find the following effective action. This is now quadratic theory, which we know how to exactly solve because it's a Gaussian theory. And this gives us everything that we expect. There's only one Nambu-Goldstone boson given by phi. And you can see that omega squared goes as k to the fourth. And the exact dispersion relation follows this expression. And I want to emphasize that just like the position operators played a dual role, phi plays a similar dual role. Phi is both the phase of the condensate wave function, but the gradient of phi also acts like displacement of the vortex lattice. And this tells you that naively you would have expected separate Goldstone bosons for the phase fluctuations and the phonons of the vortex lattice because they break different symmetries. But in the lowest Landau level, it's the same field. The fluctuations in phi encode both the phase fluctuations or the phasons of the superfluid and the phonons of the vortex lattice. There's only one Nabu-Goldstone boson. Okay, any questions about that? I'm approaching the end of my talk. Okay. I know that the talk got a bit technical towards the end, but I just want to leave you with this takeaway message, which is that if you want to coarse grain away the vortex lattice, but keep the symmetries, the translation and U1 conservation symmetries of the problem manifest, non-commutative field theory is the correct language to describe a lowest Landau level superfluid at length scales greater than the vortex separation. Okay, and the main technical technical achievement here is that this lowest Landau level coherent state path integral formalism, it provides a direct connection between the microscopic bosonic fields and this effective emergent non-commutative fields, which lets us write down an effective field theory. This has, it's very useful practically, not just as a matter of understanding. It's because the systems that we typically see this physics in, rotating Bose-Einstein condensates, they are weakly interacting systems, which means that this dictionary between the non-commutative field and the bosonic field helps us not only understand the scaling behavior, not only it helps us understand that omega goes as k squared, it also lets us predict the coefficient of the k squared if you can, if you know all the parameters of your Bose-Einstein condensate. Okay, and as future prospects, I want to leave you with a few messages. One thing I'm interested in is if you have slowly varying track potentials, we expect there to be interesting hydrodynamics, interesting superfluid hydrodynamics in this theory. It's very different from regular superfluids. The bigger picture that we're trying to understand is what is the nature of field theories manifestly restricted to the lowest Landau level. Chern-Simons HLR traditionally don't show lowest Landau level projection manifestly. We expect non-commutative field theory to be the right description there. And there's also a lot of works relating to these theories, so I don't have time to mention all of them. More practically, does this have any implication for superconductivity in ideal Chern bands? On the theory side, can we understand particle vortex duality in these non-commutative field theories? And more generally, how do we understand the relationship between UV-IR mixing in certain lowest Landau level theories and non-commutative field theory? And thank you so much for your attention. And I'm happy to take any questions. I also wanted to mention that the draft for this is almost done. And if anyone is interested to read it, I'm happy to share it with you. So just send me an email.
Right, thank you. Any questions?
I want to ask us, I know that there has already been like this, I guess, a similar work by Dam Song's group, like Nishi, etc. I remember they come out from a very like symmetric perspective, right? There's no like microscopic kind of coarse rating, whatever. So what's your like major improvement, on top of this work? Like, are you guys related, or is it an alternative result? Like, what's your relation?
Yeah, so the way I view it is like they get the right description,
Okay.
but they don't have a good microscopic. They don't have a good relationship between the microscopic degrees of freedom, which are the bosonic fields, and these non-commutative fields. So the way they justify this is through a combination of like duality arguments. So they use boson vortex duality, and they also use symmetry arguments.
I see.
So
it's a very high level kind of starting point.
Exactly.
Yeah. But you guys arrive at more or less the same result in the end, like same like effective field theory.
Exactly. So I wouldn't say the effective field theory is new. The new thing here is connecting the microscopic theory to the effective field theory. And which I think makes a lot of things clearer. And yeah. Yes.
Question regarding the microscopic like meaning of the say when you try to write down the lowest lambda level field theory, when you try to write down the F dagger operator, what does that literally mean? Or what is the basis function that F dagger is creating on?
By F dagger, you mean
Yes.
these
yes,
objects?
Yes, can you go
Oh,
back?
okay.
One page? Like.
Sorry,
go-
I
go
didn't catch that.
One page like before this one. 18. Yes.
This one?
yes.
Okay, okay. So,
Try to define that at hat like state. Is
okay,
that state the same as say you take a agricultural vertex lattice
Mhm.
state and try to translate that state? Is that the same basis state?
so it's not translation. So this is the Abrikosov vortex lattice state, right? You act on it with a general function in the lowest standard level, which can be written as a function of x hat and y hat. That gives you a new state, a new single particle state, and then you populate it with many different particle numbers, form a coherent state, and that is going to be the state.
So it's not the same as say like the guidance center basis coherent state. That's not the same.
No, it's not the same as that. Yeah,
I see. So like here, the coherent state, you mean a many-body coherent state.
many body, exactly. Yeah.
There are questions? All right, if not, let's thank the speaker again.
Okay. Thank you.
Yes, coming next week, yes. Sorry to disappoint you. Welcome.